Hi guys, this is Dr. Aeronautics, and this is the Orbiter Spaceflight Simulator Tutorials, Tutorial 6. And in this tutorial, we're going to first change this to 32 degrees. And also the main part of the tutorial, which is going to be on ballistics. If you remember last time, when we did our zoom climb in tutorial 3, I believe it was, high atmospheric flight, we were actually able to shut the engines down and then cruise up with our speed to a point when gravity would bring us back down. We're basically going to be doing that, except we're going to go really high. We're going to go so high that we'll actually go into space quite a bit, and then come back down. So we'll be going as high as a spacecraft, of course not nearly as fast as a spacecraft. And remember, when we did that, we noticed that the low atmospheric flight could only go a short distance, and then the scramjets could cross a continent, and so now I want to use ballistics to cross the ocean. So we're going to try and go from... Oh yeah, and in this I'm not actually going to attempt to land on a runway because ballistics of this sort are impossible. I'm talking about cruise missile style ballistics. Which means you enter the atmosphere at a high angle and you have absolutely no concern for heating. So we're going to fly a ballistics flight from Florida to the UK, like the London area. And we're going to do this by hopping the Atlantic Ocean. And we're going to not turn our engines on, so I will demonstrate that. So first of all, how do you go from point A to point B with your engines off? Seems impossible if you think about it. But sometimes it's one of those things right in front of your nose that you don't notice. We accomplish this with throwing. So if you want a ball to get from point A to point B, it doesn't magically teleport. You can throw it. And because the ball has inertia, it will keep moving until something like the ground stops it. Of course, on Earth we have gravity, so the ball does not just go from point A to point B, it curves from point A to point B under gravity, or otherwise goes into projectile motion, exhibiting parabolic curve behavior. We're basically going to use this to our advantage to turn our engines off. And what we're basically going to do is going to use our engines to fire ourselves up out of the atmosphere like a cannon, and then ride our velocity vector as gravity turns it to the UK. And then we'll just touch down in the London area, if possible. Okay, so there's two things that I need to explain before we take off. One is, if I zoom all the way in on the map, after we take off, you should notice a box with a line drawn out on it moving up. That box represents what would happen if our engines would shut down. That's where we would land. We would basically be contorted onto gravity, and it would be our projectile motion path, which would be represented by the line. And we're going to try and get this box to London, which is about 0 degrees longitude and I think 45-ish latitude. And we're going to accomplish that by flying in the general direction, although we cannot use the direct route because the Earth is round, which means if you go straight, eventually you're going to curve back down. So we're going to shoot for Boston. If we There's a calculator. There's a calculation for this, but I'm not going to use that. We're going to play it by ear. You basically go in the Boston direction, and the fact that the Earth is round will effectively curve your path on this rectangular projection over to northwestern Europe. The second thing, we're going to use the Orbit MFD, which is a very complex multifunctional display. And it has lots of things to say about it. But for now, I'm just going to introduce the fact that this line, this circle, or it's not a circle. This circle represents the surface of the Earth. This ellipse here, bisected by the line that you see here, represents our parabolic motion path. The reason it's not a line is because we're rotating with the Earth at 408 meters per second. So that's why it's not a straight line. If the Earth wasn't rotating, it would be a straight line. And this circle here represents the apogee, which I said earlier in our zoom climb represents the highest point of the orbit. So this can actually show us when apogee will be, and we're going to manipulate this shape so that it comes outside the Earth. Obviously right now it's not outside the Earth. That's because we're landed on it. But when we take off, it will expand outward, and then when we go forward, then it will start to balloon up towards the Earth. So just to be clear, this ellipse here, going between the center of the Earth and the surface, is what would happen if suddenly the Earth's surface ceased to exist, but the mass of the Earth was still there. As if the Earth was some sort of transmutable object that you could just flow through without having any sort of effect on the chemistry of the Earth. We would basically circle in this path because we would speed up, and then we'd get swung around the center of the Earth and then drawn back out to the edge. Again, just a hypothetical situation. When I draw this up, there's going to be two things over here that you're going to look at. APA stands for apopsis altitude. This is in kilometers. Well, first it's in meters, and then it will move to kilometers. If you look, our altitude is 2.57. Apogee is obviously the surface of the Earth because we're not moving, and it says 2.57. ALT stands for our altitude, which is also 2.57 meters. It should be the same readout as this one here. It's nothing more than the height above the ground, just like an airplane. However, remember the apogee altitude is not nearly the same as our altitude. In fact, it's going to be very different for a while because we're not going to be flying like an airplane. We're going to be flying like a ballistic projectile. And our flight is going to be significantly different this time around. So we should be ready to take off now. There's not too much involved with this. So I'm going to go to full power.
10, 9, 8. Ignition sequence has started. 6, 5, 4, 3, 2, 1, 0. We have commit and we have liftoff.
There's takeoff velocity. Okay. And again, I'm going to throttle down so that we don't end up wasting fuel. It's possible we may need it. But we're definitely going to need some, but as to how much depends on the... we shouldn't need that much. So we're going to turn until we're generally facing New York, Boston, which is probably going to be about 35 degrees. And we'll start with that and see what happens. I'm hoping that we won't have to do a mid... apologies, I forgot to set the timer. Not sure how much you guys missed, but basically, I said we're going to climb out of the atmosphere like this, which is what projectiles fly. Steep angle. Here you can see the box with the line on it. This represents what's going to happen if our engines cut projectile motion. And I can show you if we cut our engines, this will drop. There you can see we're dropping now, and that's just going to happen because of gravity pulling us down. Okay, so now what I'm going to do is switch to the orbit MFD and see how our ballistics are progressing, and they're not. This is because we're still way too low, and especially we have nearly no speed. Also, you guys know what this reaction control system does now. So I'm going to
rotation.
Turn that on and use that to assist my motion upward by holding down the 2 key, or just by using the joystick. That way I can actually throttle the amount of fuel that I use, which is not evident there. But you can hear that firing. Okay, and we're going to let the atmosphere pull our angle of attack down some. Notice I say some because this is going to be a very high angle maneuver. We're now at 100,000 feet altitude. There you can see the dot with the line on it is now moving out. We're finally starting to accumulate some sideways velocity. Let's see if it's visible on the orbit. Okay, so that's about as good as we can get it now. We're at 150,000 feet. I'm going to switch back so that you can see the static pressure is very quickly decreasing. And as you can see, nearly all of the stars are visible. And if I go outside, first I'm going to have to disable the music so that silence can be observed. And look, you see now? I'm just going to do this for a couple seconds, but the air is now having no effect on us. Look, I'll stop, and we won't move. Well, we will move a little bit. But that's because we're now at 200,000 feet. We've now surpassed the zoom climb and are truly in space in terms of altitude. Couldn't quite orbit here. Look at our projectile path marker right here. That's starting to go way out, which means I'm now going to pitch over and help it by now holding 45 degrees. And this will gradually decrease as we go faster and faster and faster. We're now at 1,000 meters per second, 2.23, 2,270 miles per hour. There's 100 kilometers, that's 62 miles. We're about 340,000 feet. I'm now going to stop giving thousands of feet because we're very, very high now. And again, remember when we did the RCS tutorial with meteor, this was 0.00. So I am now at the altitude that if I wanted to go into orbit, I could. But because we're doing ballistics, I'm going to continue cruising at this altitude, and we're basically going to jump up very high. Just check the fuel, we're doing good. And again, this line out here represents the horizon. As you'll see, there's a couple reflections of this track here. I'm going to explain what that means later on, because that is, again, to deal with orbits. And I don't want to get too complex before we actually get to orbit. This maneuver takes a very, very long time because if we were a missile trying to do this maneuver, it would be very, very much quicker because the acceleration of a missile is, super fast if you've ever seen one take off. We're only accelerating at about 1 G right now, which is very not much. Now at 2,300 meters per second, which is about 5,000 miles per hour. For reference, orbit is required to be at 8 kilometers per second or 17,500 miles per hour. Just from a crude estimate, I'm going to think that we're probably going to need to reach about 12,000 miles per hour or 5,500 meters per second in order to perform this maneuver correctly. FYI, this is a demonstration. It's not a very, in fact, it's not, what's the word I'm looking for? It's not efficient at all to fly like this. Very, very inefficient. Okay, we're at 198 kilometers, which means we're coming up on 120 miles. Check this out. I'm going to attempt to maneuver using our air flight services.
Attitude off.
So I'm turning the attitude off now. I'm going to go outside and you're going to watch the ailerons move, and based on the pressure, nothing should happen. Oh yeah, by the way, you can now see our ballistic path here is outside the surface of the Earth now, and you can see our apogee altitude is 223 kilometers. That means if we were to shut the engines off now, we would cruise for about 10 kilometers before we go back down. So, here goes. That's full downward pressure. And that's full upward pressure. I think it can be clear to say that now, finally, you can see the air flight services have zero effect on the spacecraft. That's 20 seconds being held down. Nothing happened. So this goes off now.
Rotation.
It's useless. I'm now going to refine this altitude to about 20 degrees, and I'm also going to start time accelerating because I don't want to spend too much time doing this maneuver. So again, we're just going to continue accumulating speed at altitude, 250 kilometers. Okay, we're getting close. You see it moving? I'm back at 1 time x acceleration, or I should not say time x, time acceleration. For some reason I have trouble with that. And here's the curvature thing that I told you about. It's moving over, it's curving over because the Earth is round. It looks like I got pretty close, but it might not be London. It's probably going to be Scotland. Okay, we'll stop there. Did you hear that? I just shut the engines down. Because the punch or throw of our motion is now complete. Meaning, we're a loose projectile to be able to go anywhere There is Boston. We're a loose projectile, which is now going to cruise upward. We're going to reach 395 kilometers, which is actually higher than Mir, but we're not in orbit yet. So we're basically going to shoot upwards, and then when we reach this here, we're going to peak, and then we're going to go back down. So this is basically a extended version of our zoom climb. I have plenty of reaction control system fuel, so the fun thing that we get to do now is just mess around with whatever we want. Because there's no effective pressure now, we're at 355 kilometers, which is probably about as high as the space station. Because there's no effect on pressure now, NASA would hate me for doing this, because it's very fuel inefficient. Or any mission would hate me for that matter. But I can go into crazy maneuvers that look just absolutely ridiculous now, because the air has absolutely no effect on the direction we're going. So we're actually going... Hang on. It's very difficult to... We're actually going this direction. But look at the direction we're heading. That looks really funny, doesn't it? Like, we're going in the direction that's nowhere near what we're heading. And let's see if we can find our prograde velocity vector. It should be somewhere around here. This is northeastern Canada that we're going over now. There it is. I have to get used to these engines. I'm used to the XR2 and the Delta Glider 4, which have much stronger engines. Which means I don't hold them down for nearly as long. So we're now flying in the direction of flight. And if I move this direction, you can see that the velocity vector is ever going to so slightly come down to the horizon. And it will go underneath the horizon, meaning that we would lose altitude. If I turn here, we're currently in what's called the prograde maneuver. Sorry, not the prograde maneuver, the prograde orientation. Which, remember, we tried out this prograde velocity vector thing, and that's basically what it does is it puts you in this state. Basically what it does is align you with the prograde velocity vector, which is in the direction we're heading now. And it also puts you so that your top is facing the North Pole. So we should be able to find Ursa Minor somewhere up here. There it is, towards the North Pole of your orbit, or basically as you're orbiting the Earth, it makes your wings go perpendicular to the surface of the Earth. So I'm going to hit that now, and we should be pretty close to it. It should be about here. Let's see what it decides to do. We're very close. I'd say that's probably half a degree, if not maybe a quarter of a degree off. So that was pretty darn close. Okay, have you just now noticed our velocity vectors below the horizon? And we're counting down now from the apogee, which means we've now crested and we're starting to go down. And we're going to continue going down until we meet the atmosphere. And when we meet the atmosphere, we have to realign, which means we're going to act as if we were an airplane all along. We would have to align with the velocity vector and come in like this. In real life, this would burn up your craft, but for the sake of ballistics, I'm going to fly straight into the velocity vector. Okay. So let's return to the prograde position. I feel like this is like one of those crazy exercise videos. Return to the fetal position. Okay. Should be about there. So now I'm going to first switch to this thing. I'm going to change the HUD. Earlier, when we were at Mir, we used this docking thing, and it was showing us where our prograde velocity vector relative to Mir. But we're nowhere near a space station or a satellite, and the nose cone is closed. So this is showing absolutely nothing right now. It's just unloaded. But then this other HUD is very interesting. It's the orbit HUD, and it will give information. Instead of the true airspeed, it will give you your orbit velocity, which is the same as this. And it will also give you your altitude as a function. Sorry, it will not give you your altitude. It will give what's called your radial distance, which is your distance from the center of the Earth. As you can see from here, it would basically be the distance of this solid line right here. And then it also gives, I'm sorry, that would display that here. I got very confused because we're at 6,300 meters per second, or about 14,000 miles per hour. And it's very confusing because that's very, very close to the Earth radius. So that confused me because the number was backwards. Remember, the altitude and radial distance will be displayed here, and the velocity here. So we're going to switch now. And it's also going to change our orientation of reference. So the first thing you see now, our ticker tape is now around here, and then we have a pitch ladder, which is right here. And now this says 6.715 m rate. This means 6.713 megameters radial distance, or 6,710 kilometers radial distance from the center of the Earth, with orbital velocity of this. Now watch what happens when I press prograde. It will zero all of the angles here. It will zero pitch, it will zero yaw, and it will zero bank. And remember in the other tutorial when we were explaining about X, Y, and Z coordinates being able to be applied to everything, remember we flew to Alnilam? We oriented to Alnilam. I'm going to do that again. But this time, we'll have two coordinate schemes here, so we can actually mark this and figure out what this is. So right now, and because our orbit changes, which I'll get into later, we are at X 29 degrees, Y negative 43 degrees, and Z I'm just going to guess is about, well, there we go, fix this, there we go, is now at 45 degrees. So that's basically how the coordinate system works. Okay, we're now in the, I'm going to switch back now, because we're in space, but if you say that we're in space to stay, that's wrong. As you can see, we're now in the 200s again, and that's now coming down quickly. So if you can imagine it like a hill, we're now rolling off the top of the mountain, and let me just say, we're going to come down fast. We're going to come down hard, and we're going to come down fast. Probably a couple minutes, you'll start hearing the hissing of the atmosphere. That tends to happen around 55 kilometers. You should hear a rumbling sound, which will eventually give way to roaring, and you'll see a plasma shield as we decelerate. 1 second. Apologies, just had to restart. One of the great things about this tutorial is that you can it has a cruise phase, which means See, we didn't have to use our engines, and we didn't have to pay attention at all because of that. So basically, the idea is that being that we didn't have to pay attention, we can now perform other actions. This is how astronauts aboard the International Space Station work, is because they don't have to worry about where they are, because that's controlled by gravity and their inertia, and it's entirely predictable. So because of this, it's as if you're still or not even moving, or on an Earth that's moving through space, which according to you doesn't feel like it's moving. We're now over the North Atlantic Ocean. That should be Iceland. Yep. And Scotland should begin to become... Okay. This would be Scotland here. You have the Hebrides here, and I can't quite see the Kyle of the Colch, but it should be somewhere up in here. And we're going to come down very quickly. You can now see this quickly down at 150. Okay. We need to prepare for what's called reentry, and this isn't full reentry. This would make you die in real life. But basically what I have to do is gain control when the spacecraft comes back into the atmosphere. And you saw this go horribly wrong when I did the zoom climbs in the upper atmospheric tutorial, because I forgot to leave the autopilot on. But we never turned the autopilot on. Gravity was our autopilot, so nothing to worry about. So this time we should have full control of our motion. I'm turning the air flight control surfaces on, pitching down, and I'm going to... Remember I told you this level horizon? We're going to activate that now. Actually, no. We're coming down very quickly. We're now at 83 kilometers. I'm going to switch back now. This is it. You're going to start hearing the roaring of the atmosphere. It's going to come very, very fast. It's going to be like hitting the surface of the water. And it'll go from cool to a huge plasma cloud. Look at how fast it seems like we're going. That's because we're so close to the surface. There it is. You can hear it already. You're going to have to start pitching down. Now watch our dynamic pressure go out of control. Again, this is going to kill you in real life, but to demonstrate how cruise missiles work, I'm basically going to go all the way down to the surface. Look at that. 2 megapascal, 3, 4, 6, and we're going to hit the ground like a meteor.
500.
Or no. Wow.
2500.
Look at that. Look at how fast we can turn. And look at how fast we're decelerating. 6, 7 Gs.
2500.
That's ridiculous. Well, I had a lot of fun with that. So you saw how quickly
1,000.
we decelerated. It was unbelievably fast. Like, we went from an orbital speed down to a couple hundred miles per hour in the matter of like 10 seconds. And that's exactly what a meteor
500.
does. And we're now ready to land, believe it or not. We're going to turn off the reaction control
Attitude off.
systems now.
400.
Gear down.
We're just going to land on the ground. If we could somehow do this without killing us, we'd be
300.
able to maneuver and move around so quickly around the Earth. It'd be so much fun.
200.
But unfortunately, this is not possible. We would have died several times over.
100.
And the fact that we had, I don't know, 10 megapascals worth of pressure just indicates to
50.
you that
40. 30.
it's just
20.
ridiculous.
10.
Whoops. Couldn't see the runway because there is none. But yeah, so that was just unbelievably crazy, and it was just to demonstrate ballistics, which you can now see. We landed approximately where we were supposed to, and this green line represents where we tracked from. So we followed all this, Then all of a sudden we entered the atmosphere and we made this massive turn here. And this is similar to what Galileo did. Galileo did not turn, but Galileo entered a steep angle re-entry to Jupiter like we just did. And we would have heated up to tens of thousands of degrees. Galileo, the spacecraft, the heat shield, heated up to hundreds of thousands of degrees Celsius, and the acceleration was 106 Gs. That's right, 106. That's no difference. You thought 10 Gs was bad? 106. That was really crazy, and I can demonstrate that to you in a future video. It will not be a tutorial because that is just absolutely ridiculous. But we landed near Aberdeen in Scotland, and let's see how much fuel we have left. We crossed the ocean and we burned a little bit more than half of our fuel. So mission accomplished. Join me next time for full orbital flight, in which we can go an virtually infinite distance with only a set amount of fuel. That's right, infinite distance with a finite amount of fuel. Unlock the impossible. This is Dr. Aeronautics, and I will see you guys next time for the launch into space.